Hello. In this video, we're going to be proving a small theorem that is very important in complex analysis, especially when we talk about functions of complex numbers. So if we have a rational complex valued function with real coefficients, then the conjugate of the function r of z is equal to r of the conjugate of z. So before we actually get into proving this theorem, let's talk about some preliminaries. So we have some nice properties about the conjugate of function or of complex numbers. So if I have z and w as complex numbers and lambda as a real number, we have that the conjugate of the product is the product of the conjugates. The conjugate of a quotient is the quotient of the conjugates. If I have a scalar times a complex number's conjugate, I can just pull that scalar out and I get the real number times the conjugate of the complex number. From 1, we can imply that the conjugate of z to the n is equal to the conjugate of z to the n. And finally, we can split up the conjugate over additions. So the conjugate of z plus w is the conjugate of z plus the conjugate of w. Since a rational function is just the quotient of two polynomials, before we go into the theorem itself, let's prove a small lemma about polynomials with real coefficients. So for our lemma, we're going to let f be a polynomial of a complex value, and we're going to let it have real coefficients. And what we're going to claim is that the conjugate of f of z for a complex number z is equal to f of the conjugate of z. So let's prove this. So we're going to let f be our polynomial. So then f is the sum of a sub I, z to the I, as I ranges from 0 to n. And then let's take its conjugate. So the conjugate of f of z is the conjugate of this whole sum. And we can use the properties that we have, which will be written right next to each step, to show that the conjugate of f of z is f of the conjugate of z. So we'll first split it up over addition, and then we're going to pull that constant out outside of the conjugate, and then we're going to use the fact that the conjugate of z to the I is z conjugate to the I. And that is, by definition of f of z conjugate. Now that we have this proof, it becomes really easy to prove our theorem. So our theorem states something about rational functions. So we're just going to let r of z, our rational function, be equal to f over g, two polynomials. And then we're going to take its conjugate. And we know by property 2 in our preliminaries that we can split up the conjugate over the quotient. So the conjugate of r of z is actually equal to the conjugate of f over the conjugate of g. And since f and g are both polynomials, we have that f of z bar over g of z bar is equal to f of z bar over g of z bar. And that's from the lemma that we just proved. And by definition of r, we have that is equal to r of z bar. Thank you for watching.